Good afternoon, everyone. This is Shiladitya Basu welcoming you on behalf of Fundu and Shaman Shankar. Today we have Santi Advani, co-founder of RocketML, talking about challenges of transitioning machine learning from prototyping to production-grade AI. A little bit of housekeeping. Please use Ask a Question button at any time you want. However, we will answer all the questions at the end of the presentation. As you leave, please rate the webinar, leave us a feedback, and share it with your team or network. Without further ado, here is Santi.
Thanks, Sheila. Hello, everybody. I'm Santi Advani. I'm co-founder and CTO at RocketML. I'm very excited to be here and talk about challenges of transitioning machine learning from prototyping to production-grade AI. Before starting, I would like to thank all of you on behalf of myself and my team for attending this webinar. A brief intro about myself. I have 15 years experience in design and development of fast, scalable algorithms in areas of image processing, machine learning, and physics-based simulations. In addition to that, I was involved in developing software products that are built on top of these algorithms and so that they're easy to use by users from different backgrounds. I worked as a software product manager at Intel, and I oversaw development of multiple products across 32, 22, and 14 nanometer technologies. And prior to that, got my PhD from UPenn in computational sciences and engineering, where we built algorithms to help cardiologists in early diagnosis of heart conditions. With that, the agenda for my talk is as follows. I'll start off with a background on data to value virtuous cycle and the current state of AI adoption and different challenges. In particular, I'll dig a little deeper into the concept of scalability and code portability. And I'll talk about RocketML a little bit on how we try to address these challenges when we help our customers in this transition. And I'll conclude after that. And as Sheila mentioned, please feel free to ask questions, and we'll try to address them once we're done with the presentation. There are two technology trends that form the basis for the current AI revolution. One is the Moore's law. There's an observation that transistor density will double every 2 years and has become the backbone of technology innovation over the past 4 decades. And as like any experimental curves, Moore's law is tapering, and the single chip performances have plateaued, and the cache sizes have also become are not growing anymore. But Moore's law has kind of formed the underlying backbone for the current AI revolution that we are seeing. On the other hand, we have big data revolution, which basically increase the amount of data that we collect and analyze. So according to Cisco, we are in the zettabyte era, which is 10 power 21. And there are going to be 44 billion cameras by 2022. That is approximately more than 5 cameras for every person on this planet. In addition to this, to just videos, there is text data that is being collected, there is audio, transactions, IoT sensors, and the amount of data that we are going to capture is never going to stop. So this is one of those exponentials and S-curves that is never going to plateau, and we'll continue to see these data sizes growing. So the compute and the data that is being collected is kind of given rise to this rapid revolution of AI. And the virtuous cycle is the cycle to get value from data. Companies who have mastered the below cycle have seen tremendous growth. Typically, the cycle starts on the right-hand side based on the domain, be it insurance, healthcare, manufacturing, media domain. So the domain basically dictates how we want to make use of the data. And within the domain, there is a problem that has to be defined with certain business value. This can be a new product feature. It can be a new product itself, or it can be improving existing internal processes within the organization. Right? For example, improving security, improving employee productivity, or finding problems within the organization. All these kind of form problems within a domain with certain business value. And a solution to this problem using data and machine learning is an AI solution. Once the problem is defined on the right-hand side, now the problem goes to how do we convert this problem into a machine learning problem. Right? So if I go into a little more detail into this, this is a lot more detailed description of this cycle. So once the problem is defined within a domain, now it has to be translated into a machine learning problem. Saying, is it a classification problem? Is it a regression problem? Is it even a supervised problem? And what is the kind of data that we need to collect? What is the feature engineering we need to do? What are the algorithms to use? In addition to that, there is also the variables like, is it cloud, is it on-prem, should we use CPU, GPU, and so on and so forth. So all these kind of form the intermediate cycle for training. And once we have some training models, then we try to deploy and monitor these things. So different companies are at different phases of this life cycle. So this is the data from a Gartner survey, where 59% of enterprises are in the category of knowledge gathering, investigating, and developing a strategy for AI, while 25% are in the phase of piloting these different problems that they're working on. And as you see, only 6% have actually deployed any AI solution into use. So there is a huge number of organizations that are in this transition from going from prototyping, piloting, to actually getting something into production. So when organizations are going through this kind of transition, they typically run into a few challenges. And the challenges that we are seeing when we are working with these organizations fall under 4 different categories. One is the scalability. That is, as we increase the number of resources, be it compute or be it a number of data scientists, are we getting enough productivity? Are we getting faster turnaround in terms of how fast we can deploy these models, how fast we can actually adopt AI solutions? That's one. And the other one is portability. Like, can we port our code? Can we port our current infrastructure across multiple different compute / hardware paradigms? And model diversity and hyperparameters is one big problem. There are so many different models data scientists can use today, like linear models, decision trees, neural networks, and so on and so forth. And each of them come with a vast number of hyperparameters to tune. So that becomes a lot of experimentation that they need to go through. And the last one is deployment of models. Once they have a model, like, how do they deploy? How do we monitor these models to see if they're actually doing what they're supposed to do? and also measure the value that they're getting out of these models. So these are like 4 broad challenges that organizations face. And in this talk, I'll focus and dig deeper into scalability and portability aspects of these challenges. And RocketML is a distributed machine learning platform called Spaces for Machine Learning. It's a platform that we help organizations in addressing these challenges and help them go from prototyping to production and give them tools so that they can deal with this transition from data to value and get on to the virtuous cycle of building business value in their organizations. Scalability. So within the machine learning life cycle, the 3 phases are the planning phase, the training phase, and the application deployment phase. The training phase is the phase that kind of forms the bridge between data and value. According to experts in this field, like Andrew Ng, iterating quickly is very important for research progress. That is, you have an idea, you have a problem definition that you're working with, and going from idea to an experiment, that is collecting data and training the model and seeing the result, and looping through this whole cycle as fast as you can will result in very good progress. So once a data scientist can loop through this cycle very fast, that will help them refine the problem statement, or it can help them guide to collect more data, or it can also help them improve the accuracy of the models. So those are some examples of the benefits of actually doing these iterations very fast. But there is a problem here. Problem is the training times, that is the time to go through these iterations, is growing 5 times faster than the Moore's law. That is, the compute capacity or the computational demand to train a model is growing 5 times faster. So, in this plot, the red line is basically the training times for various different models that are trained in the last 5 years. And the green line is the rate at which Moore's law is growing. Right? That kind of tells us how fast you can actually do computations. And there is a huge gap that is forming. So while the data size are increasing and Moore's law is becoming very flat, the amount of time it is taking to train is growing. So this works against the need to experiment fast and need to experiment and iterate fast for getting better models. And when one cannot train faster or the experimentation is slow, what happens is the organizations, they tend to deploy suboptimal models due to time constraints. So if a model is taking a week or multiple days to train, then there is only so much bandwidth or so much time they can wait, and they tend to deploy suboptimal models that do not have enough accuracy or haven't passed enough validation thresholds. Two, the cost is reduced data scientist productivity. Right? So once they deploy a model, or they want to train models with different parameters, or they want to experiment more, if each training iteration takes 3 or 4 days, or even 4 to 5 hours, then it's basically slowing down their productivity, and they're not able to come with enough good ideas or cannot experiment with enough ideas, and that reduces their productivity. And third one is increased compute costs. So if the training is taking too long, that can also mean that the compute capacity is not being very well used, and you would actually spend more on compute if the experimentation is slow, and we will show an example of that. So these are the costs of slow experimentation. So, so what do we do about this? So we need software that can work across multiple different compute paradigms. So there are software, like most of the open source libraries that are out there, they're built for single core or sometimes multi-core compute infrastructure. So the three paradigms that we have are single core, multi-core, and multi-node. And for toy problems or for problems that are really small, a single core implementation would work just fine. And for small problems, that is data that can actually fit into memory of a given machine, a multi-core implementation would work well. But most of the applications that an enterprise would be looking at or would be with for growing data and the need to experiment faster. So in that case, the infrastructure that has to be used is a multi-node infrastructure where you are actually stitching together a lot of machines so that you can get maximum output out of your compute. So this forms the basically a different view of the slide before. Is you have compute capacity increasing from left to right. And for AI and for the current market condition, we believe that DataCenter is the computer for machine learning. It's not a single laptop or a workstation that would be okay for prototyping, but we encourage all the organizations to adopt to cloud and the capacity that the cloud provides in solving their machine learning problems. So we call this abundant compute paradigm, and this is where majority of the organizations are. And some of them also could have access to a supercomputer, which would benefit mostly the scientific community and oil and gas exploration. But we encourage our customers to actually use solutions that are tuned for working on the cloud. So what do people use today to build prototype models? There are so many libraries, and there are new ones coming into the market in like almost every quarter. And most of these are built to work on single machines because the target for most of these libraries are data scientists who are getting trained and kind of moving from a different background to actually exploring data science and machine learning. And distributing or making these libraries work on cloud. What I mean by that is actually taking advantage of all the compute that is available in the cloud is an afterthought. That is, none of these libraries, if you take them and just use them on the cloud, to make them work on the entire cluster would take a lot of resources. So how to achieve maximum speed, right? In other words, how do we make these iterations fast? So this is the basic diagram to show what happens when we write an algorithm to solve a specific problem, say in this case, training a model. So there are two aspects that affect the speed and performance of a given algorithm. One is the data movement, that is, how is the data being moved from different parts in the compute architecture. That is, you have all the compute nodes have disks, and they have RAM, they have cache, and they have different processors. And as the data moves from top to bottom, there are compute cycles that are being used. And more the data that is moved, longer it takes for the overall problem to get solved. And that adds to one part of the compute time. And the other one is the processor time. Right? Once the data is moved to a processor, be it a CPU or a GPU, the amount of time it takes to actually do the computations itself adds to the remaining part of the time. So a very good algorithm plus a very good implementation of the algorithm takes care of both of these. That is, they try to reduce the amount of data movement from disk to the processor across all these different stages in the architecture. And they're also trying to minimize the amount of computations that happen in the processor or optimize them for best performance. And most of the open source and also commercial implementations are built for single machines. And when you look at these, there is a problem when your data doesn't fit into your memory. Right? So when, as we saw that the amount of the data size are growing, when the data doesn't fit in the RAM, what happens? And the traditional wisdom, the advice that you see is use out-of-core algorithms. That is, you can put a big enough disk, multiple terabytes of disk, and use out-of-core. That is, you basically stream data from disk to RAM, and then use RAM to CPU or the processor and solve the problem. But with this, what happens is the data movement from disk to RAM is very slow, unlike the data movement from RAM to cache and cache to CPU. So because of this, first, you're not actually using the abundant compute that you have on cloud. That is, you can actually access a lot of machines if you want to. That is, instantly you have a lot of RAM available if you add them together. And you end up wasting a lot of compute cycles moving data from disk to RAM. Because end of the day, you're paying for your processor. Right? Say if you're using a GPU, which could cost $20 on the cloud, you're basically wasting a lot of time moving data from disk to RAM while you're paying for your processor. So in those cases, the idea is to actually use distributed computing, right? So instead of using one machine where you have a limit on the amount of memory that you can get access to, you would actually stitch together a lot of machines. And together, you'll have enough memory to work with. So when you go to a distributed computing paradigm, what happens is while you still have to deal with the data movement between disk to RAM to cache to processor, you also need to take care of data moving across machines. So the optimal solution here would be one which has less computations and less data movement between the nodes and within the node. And faster processes would definitely help in this case. But the idea of actually using multiple machines together in an orchestrated fashion would have a lot of benefits. So one example for that is we've tested doing logistic regression on a terabyte data set of Criteo click-through rate data set. So here we had a billion samples, and the experiment was done using distributed machine learning on RocketML, and using out-of-core computations using LibSVM. And I think this was a TensorFlow implementation. So on the distributed machine learning solution, we used 56 instances of C4 8 extra large on AWS, where the cost of each instance is $1.6. And when we used 56 instances, cumulatively we have around 3 terabytes of memory. And we were able to solve or train a single model in 12 minutes. And the cost of that was around $17 to $18. In the case of out-of-core experiment with M4 10 extra large, which had 128 GB RAM and 5 terabyte hard disk, it took around 38 hours and costed around $77. So by using more instances, you can actually train faster. In this case, it's trained faster, around 190 times faster, and it actually costs less. Right? So a good optimal implementation of a distributed machine learning algorithm would be faster and cheaper. So we basically encourage our customers to try to use an optimal distributed machine learning solution so that they can train faster. And that's one of the things that we provide using RocketML. But distributed machine learning itself comes with its complexities. So while we manage data movement from disk to processor, there is another variable that comes into play, which is the network bandwidth. That is, how fast can we move the data between machines? And on the cloud, depending on the provider, you could get as just 10 gigs, 25 gigs, all the way till several hundreds of gigs based on the network that you use. So it is important to optimize data movement between nodes. And this is where we see that not all distributed machine learning solutions are the same. That is, depending on how all these different things are optimized, you see different results in terms of the amount of time it takes to solve a problem. So the two metrics that are important for distributed machine learning, which is needed to solve large-scale machine learning problems. One is speed, which is work log time to complete a given task. And the second one is scale. That is, optimal increase in speed as you increase the compute resources. So the traditional solution that you see, they do not focus on the scale. That is, as you increase the number of compute resources, you're actually spending more on the compute, and ideally you want to get your solution built faster. And that completely falls under the category of implementing these distributed machine learning algorithms in an optimal way so that your communication and computation are optimized. So this is an example of that. So here we compared doing singular value decomposition, which is a matrix factorization method for dimensionality reduction. It can also be used for different other applications. On a data set with 14 million samples and around 1 million features. And we tried to compute 100 singular values. And we compared the runtimes with Databricks implementation of Spark. So we start off with 4 nodes. Here, each node is a C5 2 extra large node. That is, each node on AWS has around 4 cores. And we compared the time it takes to compute these 100 singular values, both with RocketML and Spark. And we increased the compute available to solve this problem, and from 4 to 8 nodes, 8 nodes to 16, and 16 to 32. As you see, as you increase the the number of nodes that are available to solve this problem, the overall runtime or the computation time reduces in RocketML. That is, goes from 250 seconds to 200 to 150 and around 100 seconds in the case of 32. While on Spark, it basically remains pretty flat. So this study in the high performance computing world is called strong scaling. That is, you fix the problem size and you increase the compute to see if your algorithms for distributed compute are actually doing well. And the ideal scenario is optimal scaling, that is reduction in time based on the algorithm as you increase the number of compute resources. So the bottom line we want to convey here is for large data sets, out-of-core algorithms can be expensive and they can be slow. And distributed machine learning is the right tool for faster experimentation on cloud. And within distributed machine learning solutions that are out there, scalability is an important metric to assess a machine learning software. And this is one metric that is typically not looked at when comparing other solutions. And we believe that is an important metric to adopt to distributed machine learning. So moving on to code portability. Another challenge that we see that we come across is I have already written a code in Python using one language, using one library, or I've used R. I have built this prototype model. How do I port this across compute resources, right? How do I take it from to work on a single machine, single core, multi-core, to multiple nodes? And can it work across multiple data sources? Can it basically work with an object storage? My data is on S3 or Google Cloud, HDFS. Like, how do I actually access the data, and can it be built into the code of accessing this? And can it work across multiple hardware accelerators? There are new hardware accelerators coming into the market, and how can I make best use of the compute resources while not making too many changes? So here I'll just walk through this a little more. So the compute resources that we are referring to here are single core, multi-core, and multi-node. And as I mentioned, most of the libraries that are out there are built for single core and multi-core, and multi-node implementations are not straightforward, going from multi-core to multi-node. And within RocketML, the libraries that we have developed actually works across all these different paradigms, and there is no change in the code that you need to make when you go across all these different resources. So it would work on a single machine for prototyping, and also works on the on a distributed cluster with any number of nodes when you want to go for production. So that is one challenge that we addressed in our platform. The other one is data sources. So integrating the infrastructure, integrating your models with data coming from different sources, object storage like S3 or Google storage or Minio, working with different databases, SQL, NoSQL, graph databases, file storage, HDFS. So there is a seamless integration that has to happen across multiple data sources, because with cloud adoption, a lot of data is scattered around, and for different applications, data is put in different places. So in RocketML, we give integrations into different data sources. So you can access the data into your models very seamlessly with the integrations that we provide. The other knob here is the hardware accelerators. Nowadays, I mean, you have access to CPUs and GPU clusters across the cloud, and TPUs and ASICs that on Google, and there are also FPGA accelerators. While ASICs and FPGAs require a little more careful integration, moving from CPU-based clusters to GPU-based clusters should be taken care by the platform. And we pay close attention to algorithms and make sure that depending on the problem that a customer is trying to solve, we advise on which hardware to use. GPUs may not actually be the right hardware to solve every problem. They're meant for solving some problems really well. And there are problems that you can solve just with CPUs with lower total cost of ownership and get good results. So using RocketML, we make it easy to adopt to different hardware accelerators that are available for the customers on cloud or on-prem. So the idea here is the code should make use of different compute resources, be it CPU, GPU, be it single node, multi-node, or hybrid infrastructure. And it should seamlessly access data from any source and work across different accelerators. So by code portability, we mean that the data scientists who are working on translating data to value need not worry about all these intricacies of the compute infrastructure to actually do their job, and that should be part of the platform. So that this is RocketML at a glance, and how the integration that we work with. So RocketML is a machine learning platform addressing these challenges that I've been talking about, that goes on-prem or on cloud, and it works on your compute and on your storage, and the data never leaves your private instances. And users can currently access it through a command line interface or Jupyter Notebook, which is very popular across data scientists. And we're also building a user interface to make this management easy. It works across different data types. We support text, tabular, image, video, and audio data types, and work across multiple different data sources. So you can mount your S3 buckets, you can work with file systems, and we can also mount HDFS. And within RocketML, it comes with 3 parts. We provide pre-ML data processing pipelines. For example, if you're working with text data, and say you're working with millions of documents, you have to do a lot of data pre-processing, like removing stop words, doing stemming, lower casing, and working across regular expressions, and so on and so forth. So there's a long pipeline that you can build using RocketML for text data, image data, and video data. And we support multiple libraries. That is, you can actually bring in your libraries to RocketML. That is, say if you have code written in another library, we actually translate those libraries and make use of distributed compute and help you build models using your existing code. And once you can build models, we help do AutoML. Because we can iterate very fast using distributed machine learning, we can also provide very fast tuning to get your optimal hyperparameters. And we integrate well with other deployment tools so that you can deploy your models into production. So this is RocketML at a glance, and this is the stack. I don't know if you can, the font is too small, but what we have here is a little more description of the previous slide, wherein we start off with a compute infrastructure, which is on-prem or cloud, work across different data types, tabular, image, video, and text data. And for different data types, we provide different pre-processing capabilities, like data cleaning, merging, pre-processing, etc. for tabular data, image transformation, extracting objects and features, and layers within deep learning models for image and also video. And within text, we provide stopword removal, TF-IDF, stemming, and the whole scheme of things to convert a text into a document term data structure. On top of it, we have math modules and several supervised and unsupervised learning modules, classification, regression, dimensional reduction, and clustering. So that's RocketML stack. So that's kind of come to the last part of the talk. So we covered that 80% of the organizations are in the process of transitioning their workloads from prototyping to production. And two challenges that we discussed in detail today are scalability, that is, by increasing the amount of compute resources, you want to get faster results, and code portability, that is, moving across multiple different compute infrastructures and data types and data sources should be easy. And we believe a platform and set of tools should take care of those challenges and help data scientists through experimentation very fast. And the right tools can help with faster experimentation, and they can increase data scientists' productivity and also help lower overall compute costs for the organization. And with that, I'd like to thank you all very much. And if you have any questions or anything, want to try out RocketML and have a little more discussion, you can send me, Santi at rocketml.net, or my co-founder Vinay at rocketml.net, and we'll be happy to discuss more.
Thank you, Shanti. That was a very interesting presentation. We do have a couple of questions online, and I'm hoping to get some more from the audience. The first question is, I understand the need for reducing training times. This is a major problem. How about using GPU? Can all problems be solved using GPU?
Excellent question. So the GPU helps in faster processing. So let me go back to slide. So a given problem to solve training, right, to reduce training times, it's a combination of data moving across multiple parts in the architecture, disk to RAM to cache and the processor. GPUs definitely speed up, and they speed up the processing part of the training, but they do not necessarily address the remaining parts. That is, the data to RAM to cache is still a problem when you have a lot of data. So even when you're training large neural nets, the data is still being moved from CPU memory to GPU memory, and then GPU memory into GPU itself. So these actually add to a lot of cost in terms of compute cycles, and they may not be always optimal. And in some cases, we have actually shown that just by using a CPU-based cluster can actually outperform using a large GPU and actually train faster. So the answer is yes, for some problems, GPUs may help, but that is not a silver bullet, and it cannot solve all the problems. And not all problems are true for GPU, because GPUs are, again, hardware accelerators that can speed up some problems. So it's not one thing for all.
Thank you, Shanti. The next question is, RocketML is based on providing the infrastructure for machine learning model productionizing. How about online training or ML model versioning?
Yeah, so for online training, we basically provide ways to integrate, but it doesn't actually. So let me gather my thoughts here. So we help with model versioning. So we actually integrate RocketML with ML flows, so you can actually version and monitor your machine learning models. And online training itself works on the single node or single core version of RocketML, since it's built to work across multiple nodes. So with online training, one thing that we come across is the application that you want to use online training for. In some cases, online training works very well because the amount of data that is coming into your model is in the same distribution as the data that was used to train the models before. And in those cases, you can use RocketML single core or single node implementations to train faster. But in some cases, if the data that is coming in for online training is not in the distribution, then you may have to fall back on the model that is built using all the data before. And in that case, also RocketML can help because we can take advantage of large infrastructure.
That's an interesting answer.
Yeah.
Thank you. And one of the questions says, how is it different than using Google Colab with some public library like sklearn or TensorFlow?
Okay, so sklearn is built for a single machine, single node infrastructure, and it can only take advantage of one machine, that is, or one set of cores at a time. While RocketML is built for distributed computing. That is, theoretically, there is no limit on the amount of data that you can bring to RocketML in terms of training, and it will performs better than scikit-learn and TensorFlow when it comes to even single node implementations. So yeah, I hope I answered that question.
Yeah, I think so too. Anyone else? Any other questions? So in my background, I'm from the oil and gas industry, and we are kind of getting into this digitalization realm in the last couple of years. We do deal with a ton of data that comes in from the drill bits and drill stems. Have you guys come across, or have you kind of tried to expand into that domain using and stuff like that?
Yeah, so RocketML, so we're a domain agnostic infrastructure, but we actually run into these specific vertical problems. And within the IoT sensors applications, one thing we run into is anomaly detection.
Right.
For predictive maintenance. And in that case, finding anomalies before they become a real problem is very important, and we have built some algorithms to actually address that. And the other problem we see in that space is, unlike supervised learning problems, having labeled data is not always possible. And you need to basically use unsupervised learning methods or semi-supervised learning methods with very little labeled data. And those are the methods and solutions that seem to work well in the anomaly detection in oil and gas space.
Okay. So that basically goes into the, I guess, problem of overheads and costs, right? So solving the oil and gas problems are still kind of costly in terms of distributed computing and so on. Like you gave an example of two different problems, right, where you had RocketML with multiple instances and then another software with one single instance and so on. So it's kind of a similar ballpark. The oil and gas is kind of still there, right, in the sense that we haven't been able to formalize it. We haven't been able to structure it the way it would be beneficial to use things like machine learning and so on.
That's correct. Yeah. So going from a business problem and translating that domain-specific business problem into a machine learning problem is one stage that most of the companies are in. So we call it a 0 to 1 problem, like going from 0 to getting to one model. Once they hit that is when they start seeing all the scaling problems and all the challenges with actually going from the prototype first model to a production model. And that's right.
All right, that's good. That's great to know. I mean, we can use all the technologies that we can get to make things more streamlined and efficient, which is another name for cheap.
Absolutely.
We'll see how it goes. I'm hoping to get some more questions from the audience. This seemed quite a bit involved audience in terms of how they're responding. Do you have any other insights to share with us, Shanti?
So I think one of the insights I can share is the time well spent on the translation, right? For example, going from time spent here in hypothesizing a concept, hypothesizing a problem based on real business value is very important. And without just not to use machine learning for the sake of using machine learning, but it's a lot of time spent in actually translating the right business problem into machine learning problem is a very important step that has to be paid a lot of attention. Otherwise, everything downstream can become a waste. So identifying these metrics early on, saying what are the things that we want to measure across this entire pipeline is something that is important for organizations to keep in mind.
Okay, that's good. We just got another question coming in, and it kind of dovetails to what I was talking about in the oil and gas industry. The question is, can RocketML accept streaming data from a third party? And how is RocketML scaling to do that? Or I'm assuming it's planning to do that.
So we integrate with regular or traditional streaming data sets or data libraries using the APIs that they provide. And if it's a third party, I don't know if it means a proprietary streaming data set, but it's basically a matter of integrating the right APIs so that the engine has access to the data. And how does RocketML Scale do that? So we basically, given the problem size, we can estimate precisely how much compute and the resources that are needed. And given the resources or given the cloud resources, we can make maximum use of the resources needed to solve that specific problem with the streaming data coming in.
Okay, good. And one of the audience member wants to know whether you'll be able to share your slides. One part of that thing, that answer is this presentation would be available in a recorded format after the webinar is over. So you will have all the discussion that's going on and the questions that has been answered over there. However, if you're looking for the actual presentation slides, I would leave that to the speaker. Shanti, would you care to elaborate on that?
I'll check on it and I'll see if I can share.
All right. Yeah. We have a few more minutes. Get your questions in. It's an interesting discussion today. I mean, 10, 20 years ago when we went from the server-client model and then to the, I'm talking about more from a user perspective. There were these workstations, and then you'll just have the clients connecting to the servers, then you get the virtual machines coming and doing all your CFD and other computer-intensive numerical modeling. And then 20 years down the line, we see it again, and it kind of, the cycle kind of repeats, I believe.
Yeah, it does. And it also brings its own challenges with it. I mean, especially in this case, there's a whole new meaning for the concept of DevOps when it comes to deployment compared to what DevOps was for building web applications or other kind of applications on the cloud. So, yeah. So you guys do a lot of simulations, Sheila?
I used to in my previous incarnation, so yeah. There are still certain parts of the oil and gas industry, mostly in the there is our simulation portion where you basically rely on seismic data. We can't really see below the ground without relying on them. So you need to have this massive data sets that's coming in, and every well that is producing is sending you data back. And then once you go to the refineries and chemical plants, there are hundreds of sensors looking at hundreds of different variables each and every minute. So yeah, one other question comes in is, how does Docker technology help in code portability?
So yeah, Docker can definitely address the hardware independent deployment of your infrastructure or of the software. But here, in terms of portability, there are other aspects that we were referring to. That is, the code should also be able to scale with problem size. So when you use Docker, you're basically using multiple containers, and each of those containers or pods, they may not have to necessarily communicate with each other. But in the case of distributed machine learning, there should be a tight integration across different compute blocks. So we do use Docker for some aspects of it, but it doesn't necessarily address all the portability aspects that we were talking to, being able to work across multiple sources, hardware accelerators, and single core to multiple node. So yeah, hopefully that answered the question. So any other questions from the audience? Okay. So Sheila? Okay, I think the presentation is going to end in a minute. Great. I'd like to thank everyone who joined the webinar and really enjoyed talking about challenges in transitioning from prototype to production grade AI. So with that, I'm ending the webinar.